So let's talk about quadratic inequalities. Here is one x squared is greater than 9, and a very frequently occurring incorrect solution is to go, let's take the square root of both sides, and x squared greater than 9 implies that x is greater than 3. Well, here is the problem with that. What about negative 10? Negative 10 squares 100. 100 is clearly greater than 9, but we only picked up numbers bigger than 3. We didn't pick up any negative numbers. We're going to learn new techniques, and this thing that let's do the same thing to both sides, that does not work beyond linear. Okay, we're going to return to this one, but let's see now. This is a very typical quadratic inequality. Just like with equations, the first thing we're going to do is we're going to reduce one side to 0, and then we're going to attempt to factor it. I actually did completing the square. If you need help on this computation, there is a separate video for that. Okay. This particular one did factor over the integers very nicely. And this is the point when you shouldn't just go and write linear inequalities for this and that. Actually, that could work, but it's not. It's a more complicated situation, because if you want the product to be positive, then you either demand that both factors are positive or both factors are negative, and then it would work. But just saying, oh, I want both of them positive, would rule out a whole lot of other solutions where both factors are negative. But that's not what we're going to do here. Although that's a legitimate solution, maybe I'll make a video about that technique. Once one side is 0 and the other side is factored, the algebra is over, and let's go away and graph the following parabola. Let's graph y equals x plus 4 times x minus 2. Now this graph does not have to be precise. It can be a sloppy, ugly little graph. All you need to correctly represent is the orientation, namely is it something like this or something like that, and the x-intercepts. So those two are not difficult. So the x-intercepts are negative 4, 0 and 2, 0, and the leading coefficient is positive, therefore the parabola is opening upward. Okay. On this parabola, every single point has a strange property. If the first coordinate is x, then the y coordinate is x squared plus 2x minus 8. Right? Every single point does this. And so if we have to solve the inequality, x plus 4 times x minus 2 is greater than 0, that would be the same as on the graph, y is greater than 0. Right? Because on the graph, y and this product are one and the same. And so now we're looking for, first, the set of all points of whose y coordinate is positive. Let's translate from algebra to geometry. What does it mean the y coordinate is positive? That would be the algebra. The geometry belonging to that is that point is above the x-axis. So basically, everything that we see now we're interested in not all these points that we picked up, but only the x-coordinates of these points. And then when we translate that into algebra, it's kind of weird, because to the left of negative 4, those are the numbers less than negative 4. So x is less than negative 4, or x is greater than 2. You cannot combine it into a simpler statement. Also, the same solution set in interval notation. So this is the solution set. Let's return this very simple quadratic inequality. X squared is greater than 9. Let us solve this using this parabola method. So first we reduce one side to 0, and then we factor. Now this time it's the difference of squares theorem. And once you have one side 0, the other one factored, the algebra is over, let's graph this thing. Well, what do we graph? We're going to graph y equals x plus 3 times x minus 3. So again, only two things need to be indicated. It doesn't have to be a precise one. We're not interested, for example, in the vertex. All we need to know is the orientation and the x-intercepts. So the x-intercepts are negative 3, 0 and 3, 0. And the orientation is, this is a regular parabola. The leading coefficient is positive. And now we want to look for the part on this parabola. This is not the shading problem. We are just on this graph. But this graph will have a point for every x value, right? We're looking for the values of x for which this is positive. So now it does make sense, because we did pick up the negative part. If we go back, x squared is greater than 9. Basically, there is a fixed number, and we compare x squared. We did in a way that x squared should be bigger. So In short, x squared should be big. Now there are two ways to do that. Either x is a big positive number or x is a big negative number. This is the part where I ask any questions. Now let's go back to the first one. So suppose we're dealing with a quadratic inequality and we have already reduced one side to 0 and factored the other side. Then we draw the same picture. It does not matter which of the four inequality signs we're dealing with. The picture is the same. So it doesn't even matter what the inequality symbol is. We just graph the parabola. Now what the inequality symbol will determine is what part of this parabola we're looking for. Let us remind ourselves that on this curve, the y-coordinate is always x squared plus 2x minus 8. So this expression being positive on this parabola is the same as y being positive, and that is here. Now if we project this to the x-axis, if we just want to say, okay, here are the points, now I want only the x-coordinates. And I would say at first, don't rush into less or greater, just to the left, to the right, and then we're going to translate that in the next step. And so now we have to the left of -4 and to the right of 2. So in interval notation, this is negative infinity, -4, union 2, infinity. And in inequality notation, x is either less than -4 or greater than 2. Now the second one is very, very similar to the first one. The only difference that equality is allowed, which means that now we darken the circles enclosing the endpoints, indicating that the endpoints are part of the solution set. And so the rest is very, very similar. We're going to use closed intervals wherever we can. Now we can't use it at infinity or negative infinity. We can never get there. But 2 and 4 are now part of those. And as inequalities, x is less than or equal than -4, or x is greater than or equal than 2. Okay, now the inequality sign is reversed. Now we want the quadratic expression to be less than 0. That is the same as to say that on this parabola, the y-coordinates are negative, which is the same as on this parabola, the part below the x-axis. As an interval, and then in inequality notation, now this one we can write in a single compound inequality. The other one we can't. So x is locked in between -4 and 2. And the last one is of course very, very similar. We're only throwing in the endpoints in the inequality notation. And this is not so surprising if you think about it. If you look at that parabola and the 4 different cases, basically it can be summarized like this. We have -4 and 2, and you just visualize the parabola there. 2 x-intercepts split the line into 3 parts. In the middle is where the parabola was negative, and out there where it's positive. So our solution set in these cases will either look like this or this. Actually, this is how a square can be big, right? Big in the positive or big in the negative. This is how a square could be small. It has to be close to 0 to be small, and therefore it's bounded from 2 directions. And also notice that linear inequalities never give us stuff like that. They always give us just half a line, and you will see that in quadratic inequalities that's never the case. So let's see this next example. This is an example that often tricks up students who use the quadratic formula. There's nothing wrong with using the quadratic formula, but you have to understand what you're doing. In this particular case, I'm going to complete the square. And we have to stop here because we didn't get the difference of 2 squares. We got the sum of 2 squares, and that does not factor. If you were to use the quadratic formula, the discriminant would be negative. But that does not mean that this inequality has no solution. It only means that there is no 0, which is also what we got here. In the previous example, we graphed the parabola using the x-intercepts and the orientation. We can't do that here because there are no x-intercepts. Use the orientation and the vertex, right? This is the standard form. So -2, 9 is the vertex, and the orientation is, well, it's still a regular one, no negative leading coefficient. So now there could be 4 possible inequality symbols. Here, what part are we looking for the parabola? The one that's either on the x-axis or above. And that's not nothing, that's actually everything. So in this case, on paper, you can say this is the solution set, a set of all real numbers. In my open math, you're going to enter this. the same set in interval notation. So as before, there are four possibilities. Given the same quadratic expression on one side, the inequality symbol can be four different types, right? The picture is the same. Now, greater than 0, the solution set for that was everything. The y-coordinate of this parabola is always positive, right? It's also always non-negative, right? If it's always positive, then it's also always positive or 0. Now, less than 0, that's the one that has no solution. No x works here because every x works there. And so to determine that there is no 0 using the quadratic formula, that's okay, but then you will need to know how to interpret that. And that is, this parabola doesn't have an x-intercept, so it's always positive or always negative. So the solution is either nothing or everything. But you have to know which. Okay, any questions? No, you're so quiet. Okay, so let's look at this next example. This is my favorite, actually. So when we complete the square, half of negative 12 is negative 6, and x minus 6 squared happens to be this. So when we complete the square, we're going to realize that there's not much to do. We are given a complete square. This parabola has a vertex of 6, 0. This is y equals x minus 6 squared. So what part of the parabola are we looking for? We're looking for the part of the parabola that is either below the x-axis, there is none, or on the x-axis, which there is 1. This is it. So this is an inequality of whose solution set is like that of an equation. It just has one solution. X equals 6 is fine for me, but on my open math, you have to enter an interval. So how do we enter a single point as an interval? It's kind of goofy, but this is it. So that's what you need to enter in my open math. Okay, so let's go through what the four different types of inequality would give us in this case. So we have x minus 6 squared greater than 0, x minus 6 squared greater than equal than 0, x minus 6 squared less than 0, and x minus 6 squared less than equal than 0. And we just solved this last one, right? So the last one is really x equals 6. X minus 6 squared less than 0. That would mean we're looking on this picture, the part of the parabola that's below the x-axis. There is none, so this one has no solution. Right? Squares are never negative because they're always positive or 0. So this one, all real numbers are solutions of this one. Every square is positive or 0. In my open math, you're going to enter it as an interval, like so. And x minus 6 squared greater than 0 is pretty much every part of the parabola except for the vertex. So that would be from negative infinity to 6, open interval, union, 6 to infinity. Okay, so that's kind of fun. All right, a few comments. Number 1, what if we have a negative leading coefficient? So in my book, you never have to deal with that because you can either multiply both sides by -1 or just add x squared to the other side. So nicely and slowly pack stuff on the other side. Then if we add x squared and subtract 3x, we're going to get 0 is less than x squared minus 3x, which is easy to factor. We just factor out x. The x-intercepts are at 0 and 3. And we're asking, where is this expression greater than 0? So the answer is to the right of 0 and to the left of 3. So my first comment is that in case of these kind of inequalities, you never have to deal with an upside down parabola because you can just simply work on the other side. You know, adding x squared and subtracting 3x is the slow way of multiplying both sides of this by -1. But if we must, we can still do it. So let me just show you in case you want to see one. Let's factor out negative x. The multiplication backward should work. Minus x squared plus 3x. So we're good. So what do we have? We have an upside down parabola with x-intercepts 0 and 3. And now we're looking for the part that is less than 0. Well, surprise, surprise, we're going to get the same set. So that's 1. So if you have a negative leading coefficient, you can work on the other side or solve as usual, but this time you're looking at upside down parabolas. So that's one comment. The other thing I wanted to tell you is that there are three types of parabolas. The one that's pushed above the x-axis, the one that sits on the x-axis, and the one that will below the x-axis. We have seen all three cases of this, and similarly, which, as I just mentioned, you never have to really deal with, we can repeat the whole thing with upside down parabolas. 0 x-intercepts, 1 x-intercept, 2 x-intercepts. Okay. But for some people, this might be more than one case, because you can have something that x squared, what did we have? Doesn't matter. X squared minus 2x minus 15 is less than 0, say. And then when we complete the square, of course, everyone knows what this is going to be. You don't really need completing the square for this. Of course, everyone knows really how this factors, so we don't really need to complete the square. And so let's not worry about the inequality sign. If it says bigger than 0, we find this part. If it says bigger than equal, we find that part and the endpoints. And if it's less than 0, then we find what's in between. And if it's less than or equal to 0, we find what's in between and the 2 points. Now, sometimes the numbers are not as pretty as -3 and 5, but the geometry is the same. So what if we have something like x squared minus 2x minus 7? When we complete the square, we get x minus 1 squared minus 8. So this can be factored as long the picture is the same, whether the numbers are, whether this is a square or not. So this can be factored via the difference of squares theorem. When we realize 8 is a square, not a pretty one, but a square nonetheless, square root of 8 squares to 8. So then the two x-intercepts are this one. Remember we solved for 0. We applied the 0 product rule. So we're going to add 1 and subtract radical 8. So x is 1 minus square root of 8. And the other x is 1 plus root 8. And if you're not sure what these numbers look like, you can use the calculator to get them as a decimal. Square root of 8 is almost 3, right? So this is almost 4, and this is 1 minus almost 3 is almost -2, something like that. But as I said, we can also use the calculator to get decimal. Approximation is 3.82 and change. And the other one is -1.8. And then even though the numbers are intimidating, the geometry is the same. If the inequality says greater than, we find this part. If it says less than, then we find the in between. Thank you for watching.